Chapter 5. Pointers and Arrays. A pointer is a variable that contains the address of a variable. Pointers are much used in C, partly because they are sometimes the only way to express a computation, and partly because they usually lead to more compact and efficient code than can be obtained in other ways. Pointers and arrays are closely related. This chapter also explores this relationship and shows how to exploit it. The pointers have been lumped with the goto statement as a marvelous way to create impossibilito understand programs. This is certainly true when they are used carelessly, and it is easy to create pointers that point somewhere unexpected. With discipline, however, pointers can also be used to achieve clarity and simplicity. This is the aspect that we will try to illustrate. The main change in ANSI C is to make explicit the rules about how pointers can be manipulated, in effect mandating what good programmers already practice and good compilers already enforce. In addition, the type void asterisk, pointer to void, replaces char asterisk as the proper type for a generic pointer. 5.1 Pointers and Addresses. Let us begin with a simplified picture of how memory is organized. A typical machine has an array of consecutively numbered or addressed memory cells that may be manipulated individually or in contiguous groups. One common situation is that any byte can be a char, a pair of 1-byte cells can be treated as a short integer, and 4 adjacent bytes form a long. A pointer is a group of cells, often 2 or 4, that can hold an address. So if C is a char and P is a pointer that points to it, we could represent the situation this way. The unary operator and gives the address of an object, so the statement P equals and C assigns the address of C to the variable P, and P is said to point to C. The AND operator only applies to objects in memory, variables and array elements. It cannot be applied to expressions, constants, or register variables. The unary operator asterisk is the indirection or dereferencing operator. When applied to a pointer, it accesses the object the pointer points to. Suppose that x and y are integers and IP is a pointer to int. This artificial sequence shows how to declare a pointer and how to use and asterisk. Int x equals 1, y equals 2, z 10 in IP. /IP is a pointer to int /IP equals and x. /IP now points to x asterisk /y equals IP. /y is now 1 asterisk /IP equals 0. /x is now 0 /IP equals and z0. /IP now points to z0 asterisk /. The declaration of x, y, and z are what we've seen all along. The declaration of the pointer IP, int asterisk IP. Is intended as a mnemonic. It says that the expression is in the syntax of the asterisk IP int. Declaration for a variable mimics the syntax of expressions in which the variable might appear. This reasoning applies to function declarations as well. For example, double asterisk dp, ataf, char asterisk, says that in an expression asterisk dp and have values of and that the argument of atov's double is a pointer to ataf char. You should also note the implication that a pointer is constrained to point to a particular kind of object. Every pointer points to a specific data type. There is one exception. A pointer to void is used to hold any type of pointer but cannot be dereferenced itself. We'll come back to it in section 5.11. If IP points to the integer x, then can occur in any context where x could, so asterisk IP equals asterisk IP plus 10, increments asterisk IP by 10. The unary operators asterisk and bind more tightly than arithmetic operators, so the assignment y equals asterisk IP plus 1 takes whatever IP points at, adds 1, and assigns the result to y, while IP plus equals 1 increments what IP points to, as do plus IP and asterisk IP plus plus. The parentheses are necessary in this last example. Without them, the expression would increment IP instead of what it points to, because unary operators like asterisk and plus associate right to left. Finally, since pointers are variables, they can be used without dereferencing. For example, if IQ is another pointer to int, IQ equals IP copies the contents of IP into IQ, thus making IQ point to whatever IP pointed to. 5.2 Pointers and function arguments. Since C passes arguments to functions by value, there is no direct way for the called function to alter a variable in the calling function. For instance, a sorting routine might exchange two out-of-order arguments with a function called swap. It is not enough to write swap A, B, where the swap function is defined as void swap in X, int Y, / wrong * and temp equals X, X equals Y, Y equals temp. Because of call by value, swap can't affect the arguments A and B in a routine that called it. The function above swaps copies of A and B. The way to obtain the desired effect is for the calling program to pass pointers to the values to be changed. Swap and A and B, since the operator and produces the address of a variable and is a pointer to A. In itself, the swap parameters are declared as pointers and the operands are accessed indirectly through them. Void swap int *px, int py, / interchange *px and *py / temp. Temp equals *px, *px equals *py, *py equals temp. Pictorially. Pointer arguments enable a function to access and change objects in the function that called it. As an example, consider a function getInt that performs free-format input conversion by breaking a stream of characters into integer values, one integer per call. GetInt has to return the value it found and also signal end of file when there is no more input. These values have to be passed back by separate paths, for no matter what value is used for EOF, that could also be the value of an input integer. One solution is to have getInt return the end of file status as its function value, while using a pointer argument to store the converted integer back in the calling function. This is the scheme used by SCAMP as well. See section 7.4. The following loop fills an array with integers by calls to getInt. Int n, array size, getInt, int *. For n equals 0, n size and getInt, and array an equals EOF, n++. Each call sets array n to the next integer found in the input and increments n. Notice that it is essential to pass the address of array n to getInt. Otherwise, there is no way for getInt to communicate the converted integer back to the caller. Our version of returns for end of file 0 if the next input is not a number, and a getInt EOF positive value if the input contains a valid number. Hashtag include type h. Int getch void ungech int / getInt. Get next integer from input into *pn * and getInt int pn int c sign while ispace c equals getch / skip white space */ if isdigit c and c equals EOF and c equals plus and c equals dash ungech c / it is not a number * return 0 will sign equals c equals dash -1 if c equals plus c equals dash c equals getch for *pn equals 0 isdigit c equals getch *pn equals 10 *pn plus c 0 *pn equals sign if c equals OF. Ungech c return c. Throughout getInt, *pn is used as an ordinary variable. We have also used and in getch ungech, described in section 4.3, so the one extra character that must be read can be pushed back onto the input. Exercise 5-1. As written, getInt treats a plus or not followed by a digit as a valid representation of 0. Fix it to push such a character back on the input. Exercise 5-2. Write the floating point analog of what type does getFloat getInt. GetFloat return as its function value? 5.3 Pointers and arrays. In C, there is a strong relationship between pointers and arrays, strong enough that pointers and arrays should be discussed simultaneously. Any operation that can be achieved by array subscripting can also be done with pointers. The pointer version will in general be faster, but, at least to the uninitiated, somewhat harder to understand. The declaration int A10 defines an array of size 10, that is, a block of 10 consecutive objects named A0, A1. The notation refers to the ith element of the array. If is a pointer to an integer, AI pa declared as int asterisk pa, then the assignment. Pa equals and A0 sets pa to point to element 0 of A, that is, pa contains the address of A0. Now the assignment x equals asterisk pa will copy the contents of A0 into x. If points to a particular element of an array, then by definition points to the next pa plus 1 element, points I elements after pa, and points I elements before.
Das, je pa points pa plus I pa ito ao nula.
Asterisk pa plus 1 refers to the contents of is the address of and is the contents of A1. Pa plus I asterisk. Pa plus I. These remarks are true regardless of the type or size of the variables in the array A. The meaning of adding one to a pointer, and by extension, all pointer arithmetic, is that pa plus 1 points to the next object and pa plus I points to the ith object beyond pa. The correspondence between indexing and pointer arithmetic is very close. By definition, the value of a variable or expression of type array is the address of element 0 of the array. Thus, after the assignment pa equals and A0, pa, and a have identical values. Since the name of an array is a synonym for the location of the initial element, the assignment pa equals and A0 can also be written as pa equals A. Rather more surprising, at first sight, is the fact that a reference to I can also be written as an evaluating C converts it to immediately. The two forms are asterisk, A plus I.
A, I, at I, equivalent.
Applying the operator and to both parts of this equivalence, it follows that and A, I are also identical, is the address of the ith element beyond A. As the other side of this A plus I coin, if pa is a pointer, expressions might use it with a subscript, is identical to pa, I asterisk, pa plus I. In short, an array and index expression is equivalent to one written as a pointer and offset. There is one difference between an array name and a pointer that must be kept in mind. A pointer is a variable, so pa equals A and pa plus plus are legal. But an array name is not a variable. Constructions like A equals pa and A plus plus are illegal. When an array name is passed to a function, what is passed is the location of the initial element. Within the called function, this argument is a local variable, and so an array name parameter is a pointer, that is, a variable containing an address. We can use this fact to write another version of stlen, which computes the length of a string. /*stlen, return length of string s */int stlen, char *s, int n. For n equals 0, *s equals \0, s++, n++, return n. Since s is a pointer, incrementing it is perfectly legal. Has no effect on the character string s++ in the function that called, but merely increments private copy of the pointer. Strlens that means that calls like strlen hello world, / string constant / strlen array, / char array 100, / strlen ptr, / char *ptr, * all work. As formal parameters in a function definition, char s and char *s are equivalent. We prefer the latter because it says more explicitly that the variable is a pointer. When an array name is passed to a function, the function can at its convenience believe that it has been handed either an array or a pointer and manipulate it accordingly. It can even use both notations if it seems appropriate and clear. It is possible to pass part of an array to a function by passing a pointer to the beginning of the subarray. For example, if A is an array f and A2 and f A plus 2, both pass to the function f the address of the subarray that starts at within f, the A2. Parameter declaration can read f int arr or f int asterisk arr. So as far as f is concerned, the fact that the parameter refers to part of a larger array is of no consequence. If one is sure that the elements exist, it is also possible to index backwards in an array. P-1, P-2, and so on are syntactically legal and refer to the elements that immediately precede P0. Of course, it is illegal to refer to objects that are not within the array bounds. 5.4 Address arithmetic. If P is a pointer to some element of an array, then increments P to point to the next P++ element, and P plus equals I increments it to point I elements beyond where it currently does. These and similar constructions are the simplest forms of pointer or address arithmetic. C is consistent and regular in its approach to address arithmetic. Its integration of pointers, arrays, and address arithmetic is one of the strengths of the language. Let us illustrate by writing a rudimentary storage allocator. There are two routines. The first, alloc n, returns a pointer to n consecutive character positions, which can be used by the caller of alloc for storing characters. The second, affree p, releases the storage thus acquired so it can peruse later. The routines are rudimentary because the calls to affree must be made in the opposite order to the calls made on alloc. That is, the storage managed by alloc and affree is a stack or last in, first out. The standard library provides analogous functions called malloc and free that have no such restrictions. In section 8.7, we will show how they can be implemented. The easiest implementation is to have alloc hand out pieces of a large character array that we will call this array is private to, and since they deal in pointers, not allocbuff. Alloc affree. Array indices. No other routine need know the name of the array, which can be declared static in the source file containing alloc and affree, and thus be invisible outside it. In practical implementations, the array may well not even have a name. It might instead be obtained by calling malloc or by asking the operating system for a pointer to some unnamed block of storage. The other information needed is how much of allocbuff has been used. We use a pointer called that points to the next free element. When is asked for n characters, it alloc checks to see if there is enough room left, and if so, returns the current value allocbuff. Alloc of alloc, i.e., the beginning of the free block, then increments it by end to point to the next free area. If there is no room, alloc returns 0. Affree p merely sets alloc to p if p is inside allocbuff. Hashtag define alloc size 10,000 / asterisk size of available space / static char allocbuff alloc size / storage for alloc asterisk / static char alloc equals allocbuff / next free position asterisk / char alloc int n / return pointer to n characters / if allocbuff plus alloc size alloc equals n a / it fits / alloc plus equals n return alloc and /old p / tel / not enough room asterisk / return 0. Void affree char p / free storage pointed to by p asterisk / if p equals allocbuff and p allocbuff plus alloc size alloc equals p. In general, a pointer can be initialized just as any other variable can, though normally the only meaningful values are 0 or an expression involving the address of previously defined data of appropriate type. The declaration. Static char asterisk alloc equals allocbuff defines alloc to be a character pointer and initializes it to point to the beginning of allocbuff, which is the next free position when the program starts. This could also have been written static char asterisk alloc equals and allocbuff 0, since the array name is the address of the 0th element.
The test.
If allocbuff plus alloc size alloc equals n, a / asterisk it fits asterisk / checks if there's enough room to satisfy a request for n characters. If there is, the new value of alloc would be at most 1 beyond the end of allocbuff. If the request can be satisfied, alloc returns a pointer to the beginning of a block of characters. Notice the declaration of the function itself. If not, alloc must return some signal that there is no space left. C guarantees that 0 is never a valid address for data, so a return value of 0 can be used to signal an abnormal event, in this case no space. Pointers and integers are not interchangeable. 0 is the sole exception. The constant 0 may be assigned to a pointer, and a pointer may be compared with a constant 0. The symbolic constant null is often used in place of 0 as a mnemonic to indicate more clearly that this is a special value for a pointer. Null is defined in std h. We will use null henceforth.
Tests like
If alecbuff plus alecsize, alocp equals n, a / asterisk it fits * and. If p equals alecbuff and p alecbuff plus alecsize show several important facets of pointer arithmetic. First, pointers may be compared under certain circumstances. If p and q point to members of the same array, then relations like equals, etc. work properly. For example, p less than q is true if p points to an earlier element of the array than q does. Any pointer can be meaningfully compared for equality or inequality with 0. But the behavior is undefined for arithmetic or comparisons with pointers that do not point to members of the same array. There is one exception. The address of the first element past the end of an array can be used in pointer arithmetic. Second, we have already observed that a pointer and an integer may be added or subtracted. The construction p plus n means the address of the nth object beyond the one p currently points to. This is true regardless of the kind of object p points to, and is scaled according to the size of the objects p points to, which is determined by the declaration of p. If an int is 4 bytes, for example, the int will be scaled by 4. Pointer subtraction is also valid. If p and q point to elements of the same array, and then p less than q, qp plus 1 is the number of elements from p to q inclusive. This fact can be used to write yet another version of strlen ***, return length of string s */ int strlen, char *s, char *p equals s. While *p equals \0, p++, return p, s. In its declaration, p is initialized to s, that is, to point to the first character of the string. In the while loop, each character in turn is examined until the \0 at the end is seen. Because p points to characters, p++ advances p to the next character each time, and ps gives the number of characters advanced over, that is, the string length. The number of characters in the string could be too large to store in an int. The header, stuffed, h, defines a type printf_t that is large enough to hold the sign difference of 2 pointer values. If we were being cautious, however, we would use size_t for the return value of strlen to match the standard library version. Size_t is the unsigned integer type returned by the size of operator. Pointer arithmetic is consistent. If we had been dealing with floats, which occupy more storage and if p were a pointer to would advance to the next chars, float, p++ float. Thus we could write another version of that maintains instead of merely alec floats chars, by changing to throughout and all the pointer manipulations char float alec free. Automatically take into account the size of the objects pointed to. The valid pointer operations are assignment of pointers of the same type, adding or subtracting a pointer and an integer, subtracting or comparing 2 pointers to members of the same array, and assigning or comparing to 0. All other pointer arithmetic is illegal. It is not legal to add 2 pointers, or to multiply or divide or shift or mask them, or to add float or double to them, or even, except for void asterisk, to assign a pointer of one type to a pointer of another type without a cast. 5.5 character pointers and functions. A string constant, written as I am a string, is an array of characters. In the internal representation, the array is terminated with the null character, \0, so that programs can find the end. The length in storage is thus one more than the number of characters between the double quotes. Perhaps the most common occurrence of string constants is as arguments to functions, as in printf, hello, world \n, When a character string like this appears in a program, access to it is through a character pointer. Printf receives a pointer to the beginning of the character array. That is, a string constant is accessed by a pointer to its first element. String constants need not be function arguments. If pmessage is declared as char asterisk pmessage, then the statement pmessage equals now is the time assigns to pmessage a pointer to the character array. This is not a string copy. Only pointers are involved. C does not provide any operators for processing an entire string of characters as a unit. There is an important difference between these definitions. Char amessage equals now is the time / asterisk an array asterisk slash. Char pmessage equals now is the time / a pointer asterisk slash is an array just big enough to hold the sequence of characters, and that amessage \0 initializes it. Individual characters within the array may be changed, but amessage will always refer to the same storage. On the other hand, pmessage is a pointer, initialized to point to a string constant. The pointer may subsequently be modified to point elsewhere, but the result is undefined if you try to modify the string contents. We will illustrate more aspects of pointers and arrays by studying versions of two useful functions adapted from the standard library. The first function is strcpy_st, which copies the string t to the string s. It would be nice just to say s equals t, but this copies the pointer, not the characters. To copy the characters, we need a loop. The array version first. /*strcpy. Copy t to s. Array subscript version */ void strcpy char *s char *t and I equals 0 while s I equals t I equals \0 I++. For contrast, here is a version of strcpy with pointers. /*strcpy. Copy t to s. Pointer version */ void strcpy char *s char t and I equals 0 while s equals *t equals \0 s++ t++. Because arguments are passed by value, strcpy can use the parameters s and t in any way it pleases. Here they are conveniently initialized pointers, which are marched along the arrays a character at a time until the \0 that terminates t has been copied into s. In practice, strcpy would not be written as we showed it above. Experienced C programmers would prefer /*strcpy. Copy t to s. Pointer version 2 */ void strcpy char *s char *t. While *s++ equals *t++ equals \0. This moves the increment of s and t into the test part of the loop. The value of is the *t++ character that t pointed to before t was increment. The postfix doesn't change t until ++ after this character has been fetched. In the same way, the character is stored into the old s position before s is increment. This character is also the value that is compared against \0 to control the loop. The net effect is that characters are copied from t to s, up and including the terminating \0. As the final abbreviation, observe that a comparison against \0 is redundant, since the question is merely whether the expression is 0. So the function would likely be written as /*strcpy. Copy t to s. Pointer version 3 */ void strcpy char *s char t. While s++ equals *t++. Although this may seem cryptic at first sight, the notational convenience is considerable, and the idiom should be mastered because you will see it frequently in C programs. Then the standard library returns the target string as its function value. strcpy, string h. The second routine that we will examine is strcmp, st, which compares the character strings s and t and returns negative, 0 or positive if s is lexicographically less than, equal to, or greater than t. The value is obtained by subtracting the characters at the first position where s and t disagree. /*strcmp returns 0 if s less than t, 0 if s equals t, 0 if s greater than t asterisk slash. Int strcmp, char asterisk s, char asterisk t. Int I for I equals 0, s I equals t I plus plus if s I equals backslash 0, return 0, return s I t I, the pointer version of strcmp. Slash asterisk strcmp, return 0 if s less than t, 0 if s equals t, 0 if s greater than t asterisk slash and strcmp, char asterisk s, char asterisk t. 4. Asterisk s equals t, s plus plus, t plus plus, if s equals backslash 0, return 0, return asterisk s, asterisk t. Since plus plus and are either prefix or postfix operators, other combinations of asterisk and plus plus and occur, although less frequently. For example, asterisk, p decrements p before fetching the character that p points to. In fact, the pair of expressions p equals val, slash push val onto stack asterisk slash val equals p, slash pop top of stack into val asterisk slash are the standard idiom for pushing and popping a stack. See section 4.3. The header, stringed at h, contains declarations for the functions mentioned in this section, plus a variety of other string handling functions from the standard library. Exercise 5-3. Write a pointer version of the function strcat that we showed in Chapter 2. Strcat, s, t, copies the string t to the end of s. Exercise 5-4. Write the function strend s, t, which returns 1 if the string t occurs at the end of the string s, and 0 otherwise. Exercise 5-5. Write versions of the library functions and which strncpy, strcat, strncmp operate on at most the first n characters of their argument strings. For example, strncpy, s, t, n copies at most n characters of t to s. Full descriptions are in Appendix B. Exercise 5-6. Rewrite appropriate programs from earlier chapters and exercises with pointers instead of array indexing. Good possibilities include getLine, chapters 1 and 4, atwa, idoa and their variants, chapters 2, 3, and 4, reverse, chapter 3, and strindex and getup, chapter 4. 5.6 Pointer arrays. Pointers to pointers. Since pointers are variables themselves, they can be stored in arrays just as other variables can. Let us illustrate by writing a program that will sort a set of text lines into alphabetic order, a stripped-down version of the Unix program sort. In Chapter 3, we presented a shell sort function that would sort an array of integers, and in Chapter 4 we improved on it with a quick sort. The same algorithms will work, except that now we have to deal with lines of text, which are of different lengths and which, unlike integers, can't be compared or moved in a single operation. We need a data representation that will cope efficiently and conveniently with variable-length text lines. This is where the array of pointers enters. If the lines to be sorted are stored end-to-end in one long character array, then each line can be accessed by a pointer to its first character.
The
pointers themselves can be stored in an array. Two lines can be compared by passing their pointers to strcmp. When two out-of-order lines have to be exchanged, the pointers in the pointer array are exchanged, not the text lines themselves. This eliminates the twin problems of complicated storage management and high overhead that would go with moving the lines themselves. The sorting process has 3 steps. Read all the lines of input, sort them, print them in order. As usual, it's best to divide the program into functions that match this natural division, with the main routine controlling the other functions. Let us defer the sorting step for a moment and concentrate on the data structure and the input and output. The input routine has to collect and save the characters of each line and build an array of pointers to the lines. It will also have to count the number of input lines, since that information is needed for sorting and printing. Since the input function can only cope with a finite number of input lines, it can return some illegal count like -1 if too much input is presented. The output routine only has to print the lines in the order in which they appear in the array of pointers. Hashtag includes diode H. Hashtag includes string H. Hashtag define max lines 5000 / max. Hashtag lines to be sorted * char linepter max lines / pointers to text lines * /int relines char * linepter int lines void right lines char * linepter int lines void sort char * linepter int left int right / sort input lines / main int lines / number of input lines read * if lines equals relines linepter max lines equals 0 sort linepter 0 lines 1 right lines linepter lines return 0 else printf error input too big to sort \n return 1 a hashtag define maxlen 1000 * max length of any input line * and get line char * int char alloc int / read lines read input lines * /int relines char * linepter int max lines int len lines char * p line maxlen lines equals 0 while len equals get line maxlen 0 if lines equals max lines p equals alloc len equals null return -1 else line len 1 equals \0 / delete new line / strcpy p line linepter lines ++ equals p return lines / right lines right output lines * void right lines char * linepter in lines in I for I equals 0 ein lines I ++ printf %s \n linepter I. The function getLine is from section 1.9. The main new thing is the declaration for linepter. Char * linepter max lines says that linepter is an array of elements, each element of which is a pointer to a max lines that is a character pointer and is the character it points char. Linepter I linepter I 2 the first character of the ith saved text line. Since linepter is itself the name of an array, it can be treated as a pointer in the same manner as in our earlier examples, and right lines can be written instead as / right lines, right output lines * void right lines, char * linepter, in lines. While lines 0 printf %s \n linepter ++. Initially, linepter points to the first line. Each element advances it to the next line pointer while lines is counted down. With input and output under control, we can proceed to sorting. The quicksort from Chapter 4 needs minor changes. The declarations have to be modified, and the comparison operation must be done by calling strcmp. The algorithm remains the same, which gives us some confidence that it will still work. /sort, sort v left, v right, into increasing order * void sort, char * v, int left, int right. Int I last, void swap, char v, int I, int j, if left equals right, / do nothing if array contains / return, / fewer than 2 elements * swap, v, left plus right, / 2, last equals left. For I equals left plus 1, I equals right, I plus if strcmp v I v left, a 0 swap v plus last I, swap v left last, sort v left last 1, sort v last plus 1 right. Similarly, the swap routine needs only trivial changes / swap, interchange v I and v j * void swap, char * v, in I, in j, a char * temp equals v I equals v j equals temp. Since any individual element of v, alias is a character pointer, must be also, so linepter, temp1 can be copied to the other. Exercise 5-7. Rewrite to store lines in an array supplied by rather than read lines main, calling alloc to maintain storage. How much faster is the program? 5.7 multidimensional arrays. C provides rectangular multidimensional arrays, although in practice they are much less used than arrays of pointers. In this section, we will show some of their properties. Consider the problem of date conversion from day of the month to day of the year and vice versa. For example, March 1st is the 60th day of a non-leap year and the 61st day of a leap year. Let us define two functions to do the conversions. Day_of_year converts the month and day into the day of the year, and month_day converts the day of the year into the month and day. Since this latter function computes two values, the month and day arguments will be pointers. Month_day, 1988, 60, and M, and D. Sets M to 2 and D to 29, February 29th. These functions both need the same information, a table of the number of days in each month. 30 days hath September. Since the number of days per month differs for leap years and non-leap years, it's easier to separate them into two rows of a two-dimensional array than to keep track of what happens to February during computation. The array and the functions for performing the transformations are as follows. Static char datab 2, 13 equals 0, 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31 is 0, 31, 29, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31. / day_of_year. Set day of year from month and day */ int day_of_year. Int year, int month, int day, int I leap. Leap equals year %4 equals 0 and year %100 equals 0 year %400 equals 0 for I equals 1 I month I plus day plus equals datab leap I return day / month_day set month day from day of year * void month_day int year day int * month int * day and I leap. Leap equals year %4 equals 0 and year %100 equals 0 year %400 equals 0 for I equals 1 year day datab leap I plus year day dash equals datab leap I * month equals I * day equals year day. Recall that the arithmetic value of a logical expression, such as the 1 for leap, is either 0, false, or 1 true, so it can be used as a subscript of the array datab. The array has to be external to both, and so they can both datab day_of_year, month_day. Use it. We made it to illustrate a legitimate use for storing small non-character char integers. Datab is the first two-dimensional array we have dealt with. In C, a two-dimensional array is really a one-dimensional array, each of whose elements is an array. Hence, subscripts are written as datab I j / row call * rather than datab I j / wrong * other than this notational distinction. A two-dimensional array can be treated in much the same way as in other languages. Elements are stored by rows, so the rightmost subscript, or column, varies fastest as elements are accessed in storage order. An array is initialized by a list of initializers and braces. Each row of a two-dimensional array is initialized by a corresponding sublist. We started the array datab with a column of 0 so that month numbers can run from the natural 1 to 12 instead of 0 to 11. Since space is not at a premium here, this is clearer than adjusting the indices. If a two-dimensional array is to be passed to a function, the parameter declaration in the function must include the number of columns. The number of rows is irrelevant, since what is passed is, as before, a pointer to an array of rows, where each row is an array of 13 ints. In this particular case, it is a pointer to objects that are arrays of 13 ints. Thus, if the array datab is to be passed to a function f, the declaration of f would be f int datab 2, 13. It could also be f int datab 13 since the number of rows is irrelevant, or it could be F, int, asterisk dateab, 13, which says that the parameter is a pointer to an array of 13 integers. The parentheses are necessary since brackets have higher precedence than star. Without parentheses, the declaration int asterisk dateab, 13, is an array of 13 pointers to integers. More generally, only the first dimension, subscript, of an array is free. All the others have to be specified. Section 5.12 has a further discussion of complicated declarations. Exercise 5-8. There is no error checking in or remedy this defect. Day underscore of underscore year, month underscore day. 5.8 Initialization of pointer arrays. Consider the problem of writing a function month underscore name, n, which returns a pointer to a character string containing the name of the nth month. This is an ideal application for an internal static array. Month underscore name contains a private array of character strings and returns a pointer to the proper one when called. This section shows how that array of names is initialized. The syntax is similar to previous initializations / month underscore name, return name of nth month * char * month underscore name, int n. Static char name of illegal month, January, February, March, April, May, June, July, August, September, October, November, December. Return n less than 1, n greater than 12. Name 0, name n. The declaration of name, which is an array of character pointers, is the same as in the linepter sorting example. The initializer is a list of character strings. Each is assigned to the corresponding position in the array. The characters of the ith string are placed somewhere and a pointer to them is stored in name, I. Since the size of the array name is not specified, the compiler counts the initializers and fills in the correct number. 5.9 Pointers versus multidimensional arrays. Newcomers to C are sometimes confused about the difference between a two-dimensional array and an array of pointers, such as name in the example above. Given the definitions in A 10-20, in *b 10, then A3, 4, and are both syntactically legal references to a single but is AB 3, 4 int. True two-dimensional array, 200 int size locations have been set aside, and the conventional rectangular subscript calculation 20 * row plus call is used to find the element A row call. For B, however, the definition only allocates 10 pointers and does not initialize them. Initialization must be done explicitly, either statically or with code. Assuming that each element of B does point to a 20-element array, then there will be 200 ints set aside, plus 10 cells for the pointers. The important advantage of the pointer array is that the rows of the array may be of different lengths. That is, each element of B need not point to a 20-element vector. Some may point to 2 elements, some to 50, and some to none at all. Although we have phrased this discussion in terms of integers, by far the most frequent use of arrays of pointers is to store character strings of diverse lengths, as in the function month underscore name. Compare the declaration and picture for an array of pointers. Char * name equals illegal month, Jan, February, Mar. With those for a two-dimensional array, char name 15 equals illegal month, Jan, February, Mar. Exercise 5-9. Rewrite the routines and with pointers instead of day underscore of underscore year, month underscore day indexing. 5.10 Command line arguments. In environments that support C, there is a way to pass command line arguments or parameters to a program when it begins executing. When main is called, it is called with 2 arguments. The first, conventionally called argc, for argument count, is the number of command line arguments the program was invoked with. The second, argv, for argument vector, is a pointer to an array of character strings that contain the arguments, 1 per string. We customarily use multiple levels of pointers to manipulate these character strings. The simplest illustration is the program echo, which echoes its command line arguments on a single line, separated by blanks. That is, the command echo hello, world prints the output. Hello, world by convention, is the name by which the program was invoked, so is at least 1. argv0, argc. If argc is 1, there are no command line arguments after the program name. In the example above, argc is 3 and argv0, argv1 and argv2 are echo, hello, and world, respectively. The first optional argument is argv1 and the last is argc1. Additionally, the standard requires that argc be a null pointer. The first version of treats as an array of character pointers, echo argv hashtag include stio, h / echo command line arguments, first version * main, int argc, char * argv, I. For I equals 1, I argc, I++, printf, %s, argv, I argc1, printf, \n, return 0. Since argv is a pointer to an array of pointers, we can manipulate the pointer rather than index the array. This next variant is based on incrementing argv, which is a pointer to char, while argc is counted down. Hashtag include stio h / echo command line arguments, second version * main, int argc, char * argv, while argc0, printf, %s, *++ argv, argc1, printf, \n, return 0. Since argv is a pointer to the beginning of the array of argument strings, incrementing it by 1 makes it point at the original instead of each successive, ++ argv, argv1, argv0. Increment moves it along to the next argument. *argv is then the pointer to that argument. At the same time, argc is decrement. When it becomes 0, there are no arguments left to print. Alternatively, we could write the printf statement as printf, argc1, %s, *++ argv. This shows that the format argument of printf can be an expression too. As a second example, let us make some enhancements to the pattern finding program from section 4.1. If you recall, we wired the search pattern deep into the program, an obviously unsatisfactory arrangement. Following the lead of the Unix program grep, let us enhance the program so the pattern to be matched is specified by the first argument on the command line. Hashtag includes diode, h, hashtag includes string, h, hashtag define maxline 1000 and getLine, charLine at max, /find, print lines that match pattern from first arg * main, int argc, char * argv. Charline maxline int found equals 0. If argc equals 2, printf, usage, find pattern \n, else while getLine line maxline 0 if str line argv1 equals null, a printf, %s line, found ++. Return found. The standard library function str s t returns a pointer to the first occurrence of the string t in the string s, or if there is none. It is declared in null, string h. The model can now be elaborated to illustrate further pointer constructions. Suppose we want to allow two optional arguments. One says print all the lines except those that match the pattern. The second says precede each printed line by its line number. A common convention for C programs on Unix systems is that an argument that begins with a minus sign introduces an optional flag or parameter. If we choose X for accept to signal the inversion and N number, to request line numbering, then the command find X in pattern will print each line that doesn't match the pattern, preceded by its line number. Optional arguments should be permitted in any order, and the rest of the program should be independent of the number of arguments that we present. Furthermore, it is convenient for users if option arguments can be combined, as in find. NX pattern here is the program. Hashtag include stio, h, hashtag include string, h, hashtag define maxline 1000. In getLine, charLine, int max, /find, print lines that match pattern from first arg * main, Int argc, char asterisk argv, a char line max line, long lenino equals 0, int c, except equals 0, number equals 0, found equals 0. While argc 0 and asterisk plus plus argv 0 equals dash, while c equals asterisk plus plus argv 0, switch c, a case x, except equals 1, break, case n, number equals 1, break. Default, printf, find, illegal option %c backslash nc, argc equals 0, found equals -1, break, if argc equals 1 printf, usage, find x and pattern backslash n, else. While get line, max line 0, a lenino plus plus, if str line, asterisk argv, equals null, equals except, if number, printf, %ld, lenino, printf, %s, line, found plus plus. Return found, always decrement and is increment before each optional argument. At the end of the argc-argv loop, if there are no errors, argc tells how many arguments remain unprocessed and argv points to the first of these. Thus, argc should be 1 and asterisk argv should point at the pattern. Notice that plus plus argv is a pointer to an argument string, so plus plus argv 0 is its first character. An alternate valid form would be plus plus argv. Because binds tighter than asterisk and plus plus, the parentheses are necessary. Without them, the expression would be taken as asterisk plus plus argv 0.
In
fact, that is what we have used in the inner loop, where the task is to walk along a specific argument string. In the inner loop, the expression asterisk plus plus argv 0 increments the pointer argv 0. It is rare that one uses pointer expressions more complicated than these. In such cases, breaking them into 2 or 3 steps will be more intuitive. Exercise 5 to 10. Write the program expr, which evaluates a reverse Polish expression from the command line, where each operator or operand is a separate argument. For example, expr 234 plus asterisk evaluates 2 times open parenthesis 3 plus 4 close parenthesis. Exercise 5 to 11. Modify the program and written as exercises in Chapter 1 to in tab to tab accept a list of tab stops as arguments. Use the default tab settings if there are no arguments. Exercise 5 to 12. Extend and to accept the shorthand in tab to tab in tab. M plus N to mean tab stops every n columns, starting at column M. Choose convenient for the user. Default behavior. Exercise 5 to 13. Write the program tail, which prints the last n lines of its input. By default, n is set to 10, let us say, but it can be changed by an optional argument so that tail n prints the last n lines. The program should behave rationally no matter how unreasonable the input or the value of n. Write the program so it makes the best use of available storage. Lines should be stored as in the sorting program of section 5.6, not in a two-dimensional array of fixed size. 5.11 Pointers to functions. In C, a function itself is not a variable, but it is possible to define pointers to functions, which can be assigned, placed in arrays, passed to functions, returned by functions, and so on. We will illustrate this by modifying the sorting procedure written earlier in this chapter so that if the optional argument n is given, it will sort the input lines numerically instead of lexicographically. A sort often consists of 3 parts: a comparison that determines the ordering of any pair of objects, an exchange that reverses their order, and a sorting algorithm that makes comparisons and exchanges until the objects are in order. The sorting algorithm is independent of the comparison and exchange operations, so by passing different comparison and exchange functions to it, we can arrange to sort by different criteria. This is the approach taken in our new sort. Lexicographic comparison of 2 lines is done by strcmp, as before. We will also need a routine numcup that compares 2 lines on the basis of numeric value and returns the same kind of condition indication as strcmp does. These functions are declared ahead of main, and a pointer to the appropriate one is passed to sort. We have skimped on error processing for arguments, so as to concentrate on the main issues. Hashtag includes diode, H. Hashtag includes string, H. Hashtag define max lines 5000 / max. Hashtag lines to be sorted * char linepter max lines / pointers to text lines */. Int read lines char * linepter in lines. Void write lines char * linepter in lines. Void sort void linepter int left int right int comp. Void *, void *, int numcomp, char *, sort input lines * main, int argc, char argv, int lines, / number of input lines read / int numeric equals 0, /1, if numeric sort *, if argc1 and strcmp, argv1, n, equals 0, numeric equals 1, if lines equals read lines, linepter max lines, equals 0, xort, void ***, linepter 0, lines 1, int void void numeric, numcomp, strcmp, write lines, linepter, lines, return 0, else printf, input too big to sort \n, return 1. In the call to and are addresses of functions. Since they're known to sort strcmp numcomp functions, the and is not necessary in the same way that it is not needed before an array name. We have written sort so it can process any data type, not just character strings. As indicated by the function prototype, sort expects an array of pointers, 2 integers, and a function with 2 pointer arguments. The generic pointer type void * is used for the pointer arguments. Any pointer can be cast to void * and back again without loss of information, so we can call sort by casting arguments to void *. The elaborate cast of the function argument casts the arguments of the comparison function. These will generally have no effect on actual representation, but assure the compiler that all is well. / sort v left, v right into increasing order * void sort, void v. Int left, int right, int comp, void *, void *, int I last, void swap, void * v, int. If left equals right, / do nothing if array contains / return, / fewer than 2 elements * swap, v, left plus right, / 2, last equals left, for I equals left plus 1, I equals right, I plus plus. If *comp v I v left a 0 swap v plus last I swap v left last sort v left last 1 comp sort v last plus 1 right comp. The declarations should be studied with some care. The fourth parameter of sort is int *comp void void *, which says that comp is a pointer to a function that has 2 arguments and returns in void *int. The use of comp in the line if *comp v I v left 0 is consistent with the declaration, is a pointer to a function, is the function, and comp v I v left is the call to it. The parentheses are needed so the components are correctly associated. Without them, int *comp void void /wrong * says that comp is a function returning a pointer to an int, which is very different. We have already shown which compares 2 strings. Here is which strcmp numcomp compares 2 strings on a leading numeric value, computed by calling a tof. Hashtag includes lib h / numcomp. Compare S1 and S2 numerically */ int numcomp, char *s1, char *s2, double v1, v2, v1 equals a tof S1, v2 equals a tof S2. If v1, v2, return -1, else if v1, v2, return 1, else return 0. The swap function, which exchanges 2 pointers, is identical to what we presented earlier in the chapter. except that the declarations are changed to void star. Void swap, void asterisk v, and I, and j winky face. Void asterisk temp, temp equals v, I equals vj, vj equals temp. A variety of other options can be added to the sorting program. Some make challenging exercises. Exercise 5 to 14. Modify the sort program to handle R flag, which indicates sorting in reverse, decreasing order. Be sure that R works with N. Exercise 5 to 15. Add the option F to fold upper and lower case together, so that case distinctions are not made during sorting. For example, A and A compare equal. Exercise 5 to 16. Add the D directory order option, which makes comparisons only on letters, numbers, and blanks. Make sure it works in conjunction with F. Exercise 5 to 17. Add a field searching capability, so sorting may be done on fields within lines, each field sorted according to an independent set of options. The index for this book was sorted with DF for the index category and N for the page numbers. 5.12 Complicated declarations. C is sometimes castigated for the syntax of its declarations. Exercise 5 to 17. Add a field searching capability, so sorting may be done on fields within lines, each field sorted according to an independent set of options. The index for this book was sorted with DF for the index category and N for the page numbers. 5.12 Complicated declarations. C is sometimes castigated for the syntax of its declarations, particularly ones that involve pointers to functions. The syntax is an attempt to make the declaration and the use agree. It works well for simple cases, but it can be confusing for the harder ones because declarations cannot be read left to right and because parentheses are overused. The difference between int f/f, function returning pointer to int */ and int *pf /*pf, pointer to function returning int * illustrates the problem. Asterisk is a prefix operator and it has lower precedence than, so parentheses are necessary to force the proper association. Although truly complicated declarations rarely arise in practice, it is important to know how to understand them and, if necessary, how to create them. One good way to synthesize declarations is in small steps with typedef, which is discussed in section 6.7. As an alternative, in this section we will present a pair of programs that convert from valid C to a word description and back again. The word description reads left to right. The first, DCL, is the more complex. It converts a C declaration into a word description, as in these examples. Char argv, pointer to char int datab, 13. Datab, pointer to array 13 of int datab, 13 datab, array 13 of pointer to int void comp, function returning pointer to void comp, pointer to function returning void char, x, function returning pointer to array of pointer to function returning char, x3, 5, x, array 3 of pointer to function returning pointer to array 5 of char. DCL is based on the grammar that specifies a declarator, which is spelled out precisely in Appendix A, Section 8.5. This is a simplified form. DCL. Optional asterisk. S direct DCL name. DCL. Direct DCL, optional size. In words, a DCL is a direct DCL, perhaps preceded by asterisk, S. A direct DCL is a name, or a parenthesized DCL, or a direct DCL followed by parentheses, or a direct DCL followed by brackets with an optional size. This grammar can be used to parse functions. For instance, consider this declarator. Asterisk PFA will be identified as a name and thus as a direct DCL. Then is also a direct DCL. Then PFA is recognized as a DCL, so is a direct DCL. Then is a direct DCL PFA, asterisk PFA, and thus a DCL. We can also illustrate the parse with a tree like this. where direct DCL has been abbreviated to DIRDCL. The heart of the program is a pair of functions, and that parse a declaration DCL DIRDCL according to this grammar. Because the grammar is recursively defined, the functions call each other recursively as they recognize pieces of a declaration. The program is called a recursive descent parser. / DCL. Parse a declarator / void DCL, void. In NS for NS equals 0, get token, equals /* count S / NS ++, DIRDCL, while NS, 0, strcat out, pointer to. / DIRDCL, parse a direct declarator / void DIRDCL, void, then type, if token type equals / a / DCL, */ DCL, if token type equals. Printf, error missing, \n, else if token type equals name, / variable name */ strcpy, name, token, else printf, error, expected name or DCL, \n. While type equals get token, equals parens type equals brackets. If type equals parens, strcat out, function returning, else strcat out, array, strcat out, token, strcat out, of. Since the programs are intended to be illustrative, not bulletproof, there are significant restrictions on DCL. It can only handle a simple data type line char or int. It does not handle argument types and functions, or qualifiers like constant spurious blanks confuse it. It doesn't do much error recovery, so invalid declarations will also confuse it. These improvements are left as exercises. Here are the global variables and the main routine. Hashtag includes diode, h, hashtag include stringed, h, hashtag include type, h, hashtag define max token 100. Enum name, parens, brackets, void DCL, void DIRDCL, void. Int get token, void. In token type, / type of last token / char token, max token / last token string / char name, max token / identifier name * char data type, max token * data type equals char, int, etc. / char out 1000, main / convert declaration to words */ while get token equals yof, a / first token online / strcpy, data type, token, / is the data type / out, 0, equals \0, DCL, / parse rest of line */ if, token type, equals \n, printf, syntax error \n, printf, %s, %s %s \n, name, out, data type, return 0. The function getToken skips blanks and tabs, then finds the next token in the input. A token is a name, a pair of parentheses, a pair of brackets perhaps including a number or any other single character. In getToken void, / return next token */. In C, getch void, void int, char *p equals token while C equals getch. Equals C equals \t, if C equals getch, equals strcpy, token, return token type equals parens. Else getch C, return token type equals. Else if C equals. For *p++ equals C, *p++ equals getch, equals. P equals \0, return token type equals brackets, else if isalpha C, for P++ equals C, isalnum C equals getch. *p++ equals C, *p equals \0, getch C, return token type equals name, else return token type equals C, A, and are discussed in Chapter 4. Getch getch. Going in the other direction is easier, especially if we do not worry about generating redundant parentheses. The program uncle converts a word description like x is a function returning a pointer to an array of pointers to functions returning char, which we will express as x, asterisk, asterisk, char2. Char, asterisk, asterisk x. The abbreviated input syntax lets us reuse the function. Also uses the same getToken uncle external variables as DCL does. / asterisk uncle. Convert word descriptions to declarations asterisk / main, int type, char temp, max token, while get token equals yof, strcpy out token, while type equals get token equals \n. If type equals parens type equals brackets, strcat out token. Else if type equals asterisk, a sprints temp, asterisk %s, out, strcpy out temp. Else if type equals name, a sprints temp, %s, token out, strcpy out temp. Else printf, invalid input at %s \n, token, return 0. Exercise 5-18. Make DCL recover from input errors. Exercise 5-19. Modify uncle so that it does not add redundant parentheses to declarations. Exercise 5-20. Expand DCL to handle declarations with function argument types, qualifiers like const, and so on. Chapter 6 Structures. A structure is a collection of one or more variables, possibly of different types, grouped together under a single name for convenient handling. Structures are called records in some languages, notably Pascal. Structures help to organize complicated data, particularly in large programs, because they permit a group of related variables to be treated as a unit instead of as separate entities. One traditional example of a structure is the payroll record. An employee is described by a set of attributes such as name, address, social security number, salary, etc. Some of these in turn could be structures. A name has several components, as does an address and even a salary. Another example, more typical for C, comes from graphics. A point is a pair of coordinate, a rectangle is a pair of points, and so on. The main change made by the ANSI standard is to define structure assignment. Structures may be copied and assigned to, passed to functions, and returned by functions. This has been supported by most compilers for many years, but the properties are now precisely defined. Automatic structures and arrays may now also be initialized. 6.1 Basics of Structures. Let us create a few structures suitable for graphics. The basic object is a point, which we will assume has an x-coordinate and a y-coordinate, both integers. The two components can be placed in a structure declared like this: struct point int x, int y. The keyword struct introduces a structure declaration, which is a list of declarations enclosed in braces. An optional name called a structure tag may follow the word struct, as with point here. The tag names this kind of structure and can be used subsequently as a shorthand for the part of the declaration in braces. The variables named in a structure are called members. A structure member or tag and an ordinary, i.e. non-member, variable can have the same name without conflict, since they can always be distinguished by context. Furthermore, the same member names may occur in different structures, although as a matter of style one would normally use the same names only for closely related objects. A struct declaration defines a type. The right brace that terminates the list of members may be followed by a list of variables, just as for any basic type. That is, struct x, y, z is syntactically analogous to int x, y, z, in the sense that each statement declares x, y, and z to be variables of the name type and causes space to be set aside for them. A structure declaration that is not followed by a list of variables reserves no storage. It merely describes a template or shape of a structure. If the declaration is tagged, however, the tag can be used later in definitions of instances of the structure. For example, given the declaration of point above, struct point defines a variable point which is a structure of type A. Structure can be initialized struct point by following its definition with a list of initializers, each a constant expression for the members. Struct maxed equals 320, 200. An automatic structure may also be initialized by assignment or by calling a function that returns a structure of the right type. A member of a particular structure is referred to in an expression by a construction of the form structure name, member. The structure member operator connects the structure name and the member name. To print the coordinates of the point, for instance, printf, %d, %d, ptx, pty, or to compute the distance from the origin 0, 0 to point, double dist, sqrt, double, dist equals sqrt, double, ptx asterisk ptx plus, double, pty asterisk pty. Structures can be nested. One representation of a rectangle is a pair of points that denote the diagonally opposite corners, struct rect struct point 1, struct point 2. The rect structure contains two structures. If we declare as point screen struct rect screen, then screen de point 1 x refers to the x coordinate of the point 1 member of screen. 6.2 Structures and functions. The only legal operations on a structure are copying it or assigning to it as a unit, taking its address with and accessing its members. Copy and assignment include passing arguments to functions and returning values from functions as well. Structures may not be compared. A structure may be initialized by a list of constant member values. An automatic structure may also be initialized by an assignment. Let us investigate structures by writing some functions to manipulate points and rectangles. There are at least three possible approaches: pass components separately, pass an entire structure, or pass a pointer to it. Each has its good points and bad points. The first function will take two integers and return a structure. Make point, ** make point. Make a point from x and y components */ struct point make point. Int x, int y, a struct point temp. Temp, x equals x. Temp y equals y, return temp. Notice that there is no conflict between the argument name and the member with the same name. Indeed, the reuse of the names stresses the relationship. Makepoint can now be used to initialize any structure dynamically or to provide structure arguments to a function, struct rect screen, struct point middle, struct point makepoint, int. Screen PT 1 makapoint, 0,0, screen PT 2 makapoint, xmax, x, midle makapoint, screen PT 1 x, screen PT 2 x, 2, screen PT 1 y, screen PT 2 y, 2. The next step is a set of functions to do arithmetic on points. For instance, / add points. Add 2 points * struct add point, struct point p1, struct point p2, a p1.x plus equals p2.x, p1.y plus equals p2.y. Return p1. Here both the arguments and the return value are structures. We increment the components in P1 rather than using an explicit temporary variable to emphasize that structure parameters are passed by value, like any others. As another example, the function tinrect tests whether a point is inside a rectangle. Where we have adopted the convention that a rectangle includes its left and bottom sides but not its top and right sides / tinrect, return 1 if PNR, 0 if not */. In tinrect, struct point p, struct rect r, return p, x equals r to point 1 x and p, x less than r to point 2 x and p, y equals r point 1 y and p, y less than r point 2 y. This assumes that the rectangle is presented in a standard form where the point 1 coordinates are less than the point 2 coordinates. The following function returns a rectangle guaranteed to be in canonical form, #define min, a, b, #define max, a, b, / canon rect, canonicalized coordinates of rectangle */ struct rect canon rect, struct rect r, a struct rect temp. Temp PT 1 x min, PT 1 x, PT 2 x, temp PT 1 y min, PT 1 y, PT 2 y, temp PT 2 x max, PT 1 x, PT 2 x, temp PT 2 y max, PT 1 y,
EPT2Y, return temp.
If a large structure is to be passed to a function, it is generally more efficient to pass a pointer than to copy the whole structure. Structure pointers are just like pointers to ordinary variables. The declaration. Struct point asterisk pp says that pp is a pointer to a structure of type if points to a struct point. pp point structure is the structure and are the members. To use pp, we pp.x asterisk pp.y might write, for example, struct point origin asterisk pp. pp equals and origin, printf. Origin is %d \n asterisk pp x asterisk pp.y. The parentheses are necessary in asterisk pp x because the precedence of the structure member operator is higher than star. The expression asterisk pages x means asterisk pages x, which is illegal here because x is not a pointer. Pointers to structures are so frequently used that an alternative notation is provided as a shorthand. If P is a pointer to a structure, then P dash, member of structure, refers to the particular member. So we could write instead printf. Origin is %d \n pp dash x pp dash y, both. And dash, associate from left to right. So if we have struct rect r, asterisk rp equals and r. 10 for expressions are equivalent. rpt1x, rppt1x, rpt1x, rppt1x. The structure operators and dash, together with for function calls and for subscripts, are at the top of the precedence hierarchy and thus bind very tightly. For example, given the declaration, struct int len char asterisk str asterisk p, then plus p dash len increments len, not p, because the implied parenthesization is parentheses can be plus p dash len. Used to alter binding, increments p before accessing and plus p dash a len p dash a len increments p afterward. This last set of parentheses is unnecessary. In the same way, fetches whatever points to. Increments after asterisk p dash str asterisk p dash str plus str accessing whatever it points to, just like increments whatever points s p dash str plus str to. And increments p after accessing whatever points to. Asterisk p dash str 6.3 arrays of structures. Consider writing a program to count the occurrences of each C keyword. We need an array of character strings to hold the names and an array of integers for the counts. One possibility is to use two parallel arrays, keyword and key count, as in char asterisk keyword and keys, int key count and keys. But the very fact that the arrays are parallel suggests a different organization, an array of structures. Each keyword is a pair, char asterisk word, in coot. And there is an array of pairs. The structure declaration struct key char asterisk word, in count. Keytab and keys declares a structure type, defines an array of structures of this type, and sets aside keytab storage for them. Each element of the array is a structure. This could also be written struct key char asterisk word, in count. Struct keytab and keys. Since the structure keytab contains a constant set of names, it is easiest to make it an external variable and initialize it once and for all when it is defined. The structure initialization is analogous to earlier ones. The definition is followed by a list of initializers enclosed in braces. Struct key char asterisk word, int count. Keytab equals auto, 0, break, 0, case, 0, char, 0, const, 0, continue, 0, default, 0, /asterisk, asterisk / and signed, 0, void, 0, volatile, 0, while, 0. The initializers are listed in pairs corresponding to the structure members. It would be more precise to enclose the initializers for each row or structure in braces, as in auto, 0, break, 0, case 0. But inner braces are not necessary when the initializers are simple variables or character strings and when all are present. As usual, the number of entries in the array key tab will be computed if the initializers are present and the is left empty. The keyword counting program begins with the definition of key tab. The main routine reads the input by repeatedly calling a function getWord that fetches one word at a time. Each word is looked up in key tab with a version of the binary search function that we wrote in Chapter 3. The list of keywords must be sorted in increasing order in the table. Hashtag includes diode H, hashtag include type H, hashtag includes string H, hashtag define max word 100 in getWord, char asterisk int bin search, char asterisk struct key int / count C keywords asterisk / main. Enten, farvort mas wort. While getWord, word, max word, equals EOF, if iselfa word 0, if n equals bin search, word, key tab and KUS, equals 0, key tab, and count plus plus, for n equals 0, n and KUS. n plus plus if key tab and count 0, printf, %4d%s \n, key tab and count, key tab and word, return 0, a / bin search, find word in tab 0, tab, and 1 * in bin search, char * word, struct key tab, in n. In cond, int low, high, mid, low equals 0, high equals n1, while low equals high, mid equals low plus high /2, if cond equals strcmp, word, tab, mid, word, a 0, high equals mid 1, else if cond 0, low equals mid plus 1, else. Return mid, return -1. We will show the function getWord in a moment. For now, it suffices to say that each call to getWord finds a word, which is copied into the array named as its first argument. The quantity is the number of keywords in, although we could count this by nkys key tab. Hand, it's a lot easier and safer to do it by machine, especially if the list is subject to change. One possibility would be to terminate the list of initializers with a null pointer, then loop along key tab until the end is found. But this is more than is needed, since the size of the array is completely determined at compile time. The size of the array is the size of one entry times the number of entries, so the number of entries is just size of key tab / size of struct key. C provides a compile time unary operator called sizeof that can be used to compute the size of any object. The expressions size of object and size of type name yield an integer equal to the size of the specified object or type in bytes. Strictly, sizeof produces an unsigned integer value whose type, size_t, is defined in the header, stef, h. An object can be a variable or array or structure. A type name can be the name of a basic type like int or double, or a derived type like a structure or a pointer. In our case, the number of keywords is the size of the array divided by the size of one element. This computation is used in a #define statement to set the value of nkys. #define nkys, size of key tab / size of struct key. Another way to write this is to divide the array size by the size of a specific element. #define nkys, size of key tab / size of key tab 0. This has the advantage that it does not need to be changed if the type changes. It cannot be used in a line because the preprocessor does not parse type names. Size of #if, but the expression in the #define is not evaluated by the preprocessor, so the code here is legal. Now for the function we have written a more general than is necessary for getWord. GetWord this program, but it is not complicated. GetWord fetches the next word from the input, where a word is either a string of letters and digits beginning with a letter or a single non-white space character. The function value is the first character of the word, or EOF for end of file, or the character itself if it is not alphabetic. / *getWord, get next word or character from input */ in getWord, char *word, int lim, ANSI C, getch, void, void int, char asterisk w equals word, while if space c equals getch, if c equals yof, asterisk w plus plus equals c. If isalpha c w equals \0, return c, 4, lim 0, w plus plus if isalnum w equals getch, ungetch, asterisk w, break, asterisk w equals \0, return word 0. Uses the and that we wrote in Chapter 4. When the collection of an get word getch ungetch alphanumeric token stops, get word has gone one character too far. The call to ungetch pushes that character back on the input for the next call. Get word also uses ispace to skip whitespace, isalpha to identify letters, and isalnum to identify letters and digits. All are from the standard header, type H. Exercise 6-1. Our version of getWord does not properly handle underscores, string constants, comments, or preprocessor control lines. Write a better version. 6.4 Pointers to structures. To illustrate some of the considerations involved with pointers to and arrays of structures, let us write the keyword counting program again, this time using pointers instead of array indices. The external declaration of need not change, but and do need keydab main bin search modification. Hashtag includes diode H, hashtag include type H, hashtag includes string H, hashtag define maxword 100. In getWord, char asterisk int, struct key asterisk bin search, char asterisk, struct key int, / count c keywords, pointer version asterisk / main, a char word, maxword, struct key asterisk p. While getWord, word, maxword, equals yof if isalpha word 0, if p equals bin search, word, keydab, and kys, equals null, p dash count plus plus, 4, p equals keydab, p keydab plus and kys. P plus plus if p dash count 0, printf, %4d %s \n, p dash count, p dash word, return 0, / bin search, find word in tab 0. Tab, and 1 * struct key * bin search, char * word, struct key * tab, and n. In cond, struct key * low equals and tab 0, struct key * high equals and tab, and struct key * mid, while low, high, mid equals low plus, high low, /2, if cond equals strcmp, word, mid dash word, 0. High equals mid, else if cond 0, low equals mid plus 1, else return mid, return null. There are several things worthy of note here. First, the declaration of bin search must indicate that it returns a pointer to struct key instead of an integer. This is declared both in the function prototype and in if finds the word, it returns a pointer to it. If bin search it fails, it returns null. Second, the elements of keydab are now accessed by pointers. This requires significant changes in bin search. The initializers for and are now pointers to the beginning and just past the end of the low-high table. The computation of the middle element can no longer be simply mid equals low plus high, /2 * wrong * because the addition of pointers is illegal. Subtraction is legal, however, so high-low is the number of elements, and thus mid equals low plus high-low, /2 sets mid to the element halfway between and low-high. The most important change is to adjust the algorithm to make sure that it does not generate an illegal pointer or attempt to access an element outside the array. The problem is that n-tab, -1 and n-tab, n, are both outside the limits of the array tab. The former is strictly illegal, and it is illegal to dereference the latter. The language definition does guarantee, however, that pointer arithmetic that involves the first element beyond the end of an array, that is, n-tab, n, will work correctly. In main we wrote, for p equals keydab, p keydab plus nkys. P++, if p is a pointer to a structure, arithmetic on p takes into account the size of the structure, so p++ increments p by the correct amount to get the next element of the array of structures. and the test stops the loop at the right time. Don't assume, however, that the size of a structure is the sum of the sizes of its members. Because of alignment requirements for different objects, there may be unnamed holes in a structure. Thus, for instance, if a char is 1 byte and an int 4 bytes, the structure struct char c int I might well require 8 bytes, not 5. The size of operator returns the proper value. Finally, an aside on program format. When a function returns a complicated type like a structure pointer, as in struct key asterisk bin search, char asterisk word, struct key asterisk tab, int n, the function name can be hard to see and to find with a text editor. Accordingly, an alternate style is sometimes used. Struct key asterisk bin search, char asterisk word, struct key asterisk tab, int n. This is a matter of personal taste. Pick the form you like and hold to it. 6.5 Self-referential structures. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. Since the list of words isn't known in advance, we can't conveniently sort it and use a binary search. Yet we can do a linear search for each word as it arrives to see if it's already been seen. The program would take too long. More precisely, its running time is likely to grow quadratically with the number of input words. How can we organize the data to copy efficiently with a list or arbitrary words? One solution is to keep the set of words seen so far sorted at all times by placing each word into its proper position in the order as it arrives. This shouldn't be done by shifting words in a linear array, though that also takes too long. Instead, we will use a data structure called a binary tree. The tree contains one node per distinct word. Each node contains a pointer to the text of the word, a count of the number of occurrences, a pointer to the left child node, a pointer to the right child node. No node may have more than 2 children. It might have only 0 or 1. The nodes are maintained so that at any node the left subtree contains only words that are lexicographically less than the word at the node, and the right subtree contains only words that are greater. This is the tree for the sentence, "Now is the time for all good men to come to the aid of their party," as built by inserting each word as it is encountered. To find out whether a new word is already in the tree, start at the root and compare the new word to the word stored at that node. If they match, the question is answered affirmatively. If the new record is less than the tree word, continue searching at the left child, otherwise at the right child. If there is no child in the required direction, the new word is not in the tree, and in fact the empty slot is the proper place to add the new word. This process is recursive, since the search from any node uses a search from one of its children. Accordingly, recursive routines for insertion and printing will be most natural. Going back to the description of a node, it is most conveniently represented as a structure with 4 components. Struct node / the tree node, * / char word, / points to the text */ int count, / number of occurrences * / struct node left, / left child * struct node right, / right child */. This recursive declaration of a node might look chancy, but it's correct. It is illegal for a structure to contain an instance of itself, but struct node * left declares left to be a pointer to a node itself. Tnode. Occasionally, one needs a variation of self-referential structures, 2 structures that refer to each other. The way to handle this is struct t, struct sp, / p points to an s */, struct s, struct tq, / q points to a t */. The code for the whole program is surprisingly small, given a handful of supporting routines like getWord that we have already written. The main routine reads words with getWord and installs them in the tree with addTree. Hashtag includes diode h, hashtag include type h, hashtag includes string h. Hashtag define maxword 100 struct tnode * addTree, struct tnode * char *, void tree print, struct tnode *, int getWord char int, /word frequency count */ main. Struct to node * root. Char word, max word, root equals null, while get word, max word, equals yof if iselfa, word 0, root equals add tree root word, tree print root, return 0. The function is recursive. A word is presented by to the top level, the root, of add tree main the tree. At each stage, that word is compared to the word already stored at the node and is percolated down to either the left or right subtree by a recursive call to add tree. Eventually, the word either matches something already in the tree, in which case the count is increment, or a null pointer is encountered, indicating that a node must be created and added to the tree. If a new node is created, addTree returns a pointer to it, which is installed in the parent node. Struct to node * talloc void char * strutup char / addTree. Add a node with w at or below p */ struct tree node * addTree. Struct to node *p char * w in cond. If p equals null, a / a new word has arrived / p equals talloc / make a new node * p dash word equals strutup w p dash count equals 1 p dash left equals p dash right equals null. Else if cond equals strcmp w p dash word equals 0 p dash count ++ / repeated word / else if cond 0 / less than into left subtree * p dash left equals addTree p dash left w. Else * greater than into right subtree * p dash right equals addTree p dash right w. Return p. Storage for the new node is fetched by a routine talloc, which returns a pointer to a free space suitable for holding a tree node, and the new word is copied into a hidden space by strutup. We will discuss these routines in a moment. The count is initialized, and the two children are made null. This part of the code is executed only at the leaves of the tree when a new node is being added. We have, unwisely, omitted error checking on the values returned by strutup and talloc. Treeprint prints the tree in sorted order. At each node, it prints the left subtree, all the words less than this word, then the word itself, then the right subtree, all the words greater. If you feel shaky about how recursion works, simulate treeprint as it operates on the tree shown above. / treeprint. In order print of tree p * /void treeprint, struct to node * p, if p equals null. Treeprint p dash left, printf, %4d %s \n, p dash count, p dash word, treeprint p dash right. A practical note. If the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too much. As a worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree that do not suffer from this worst-case behavior, but we will not describe them here. Before leaving this example, it is also worth a brief digression on a problem related to storage allocators. Clearly, it's desirable that there be only one storage allocator in a program, even though it allocates different kinds of objects. But if one allocator is to process requests for, say, pointers to chars and pointers to struct nodes, two questions arise. First, how does it meet the requirement of most real machines that objects of certain types must satisfy alignment restrictions? For example, integers often must be located at even addresses. Second, what declarations can cope with the fact that an allocator must necessarily return different kinds of pointers? Alignment requirements can generally be satisfied easily, at the cost of some wasted space, by ensuring that the allocator always returns a pointer that meets all alignment restrictions. The alloc of Chapter 5 does not guarantee any particular alignment, so we will use the standard library function malloc, which does. In Chapter 8, we will show one way to implement malloc. The question of the type declaration for a function like malloc is a vexing one for any language that takes its type checking seriously. In C, The proper method is to declare that malloc returns a pointer to void, then explicitly coerce the pointer into the desired type with a cast. Malloc and related routines are declared in the standard header stlib h. Thus, talloc can be written as hashtag include stlib h / talloc. Make a tnode */ struct tnode * talloc void. Return struct tnode * malloc size of struct tnode. Struct merely copies the string given by its argument into a safe place, obtained by a call on malloc. Char * struct char s / make a duplicate of s * char * p. P equals char malloc stlen s +1 / +1 4 \0 * if p equals null strcpy p s return p. Malloc returns null if no space is available. Struct passes that value on, leaving handling to its caller. Storage obtained by calling may be freed for reuse by calling see chapters 8 malloc free and 7. Exercise 6-2. Write a program that reads a C program and prints in alphabetical order each group of variable names that are identical in the first 6 characters, but different somewhere thereafter. Don't count words within strings and comments. Make 6 a parameter that can be set from the command line. Exercise 6-3. Write a cross-referencer that prints a list of all words in a document and, for each word, a list of the line numbers on which it occurs. Remove noise words like the, and so on. Exercise 6-4. Write a program that prints the distinct words in its input sorted into decreasing order of frequency of occurrence. Precede each word by its count. 6.6 Table Lookup. In this section, we will write the innards of a table lookup package to illustrate more aspects of structures. This code is typical of what might be found in the simple table management routines of a macro processor or a compiler. For example, consider the hashtag define statement. When a line like hashtag define in1 is encountered, the name in and the replacement text1 are stored in a table. Later, when the name in appears in a statement like state equals in, it must be replaced by 1. There are 2 routines that manipulate the names and replacement texts. Install s t records the name s and the replacement text t in a table. S and t are just character strings. Lookup searches for s in the table and returns a pointer to the place where it was found, or null if it wasn't there. The algorithm is a hash search. The incoming name is converted into a small non-negative integer, which is then used to index into an array of pointers. An array element points to the beginning of a linked list of blocks describing names that have that hash value. It is null if no names have hash to that value. A block in the list is a structure containing pointers to the name, the replacement text, and the next block in the list. A null next pointer marks the end of the list. Struct and list / table entry */struct and list next /next entry in chain */char name /define name */char defn /replacement text */. The pointer array is just hashtag define #size 101. Static struct and list *hashdab #size. / pointer table * the hashing function, which is used by both lookup and install, adds each character value in the string to a scrambled combination of the previous ones and returns the remainder modulo the array size. This is not the best possible hash function, but it is short and effective. /*hash. Form hash value for string s */ unsigned hash char *s unsigned hash val. 4. Hash val equals 0 *s equals \0 s++ hash val equals *s plus 31 hash val. Return hash val % #size. Unsigned arithmetic ensures that the hash value is non-negative. The hashing process produces a starting index in the array hashdab. If the string is to be found anywhere, it will be in the list of blocks beginning there. The search is performed by lookup. If lookup finds the entry already present, it returns a pointer to it. If not, it returns null. /*lookup Look for S in hashdab asterisk slash struct and list asterisk lookup char asterisk S struct and list asterisk NP. 4. NP equals hashdab hashes. NP equals null. NP equals NP dash next if strcmp S NP dash name equals 0. Return NP / asterisk found asterisk slash return null slash asterisk not found asterisk / The for loop in lookup is the standard idiom for walking along a linked list. 4. PTR equals head. PTR equals null. PTR equals PTR dash next. Install uses lookup to determine whether the name being installed is already present. If so, the new definition will supersede the old one. Otherwise, a new entry is created. Install returns null if, for any reason, there is no room for a new entry. Struct and list asterisk lookup char asterisk strutup char slash install put name defn and hashdab asterisk slash struct and list asterisk install char asterisk name char asterisk defn a struct and list asterisk np and signed hashval. If np equals lookup name equals null a / asterisk not found asterisk slash np equals struct and list malloc size of np. If np equals null np dash name equals strutup name equals null. Return null hashval equals hash name np dash next equals hashdab hashval equals np. Else / asterisk already there asterisk slash free void np dash defn slash free previous defn asterisk slash if np dash defn equals strutup defn equals null return np. A exercise 6-5. Write a function undef that will remove a name and definition from the table maintained by lookup and install. Exercise 6-6. Implement a simple version of the hashtag define processor, i.e. no arguments, suitable for use with C programs based on the routines of this section. You may also find getch and ungetch helpful. 6.7 Typedef. C provides a facility called typedef for creating new data type names. For example, the declaration. Typedef int length makes the name length a synonym for the type can be used in declarations. Int length casts, etc. in exactly the same ways that the int type can be. Length len, max len, length asterisk lengths. Similarly, the declaration typedef char asterisk string makes string a synonym for or character pointer, which may then be used in char asterisk declarations and casts. String p, lenepter, maxlines, alloc, int strcmp, string, p equals string, malloc, 100. Notice that the type being declared in a typedef appears in the position of a variable name, not right after the word syntactically, is like the storage classes typedef extern, etc. We have used capitalized names to make them stand out. Static typedefs. As a more complicated example, we could make typedefs for the tree node shown earlier in this chapter. Typedef struct node treepter, typedef struct node / the tree node, asterisk / char word, / points to the text / int count, / number of occurrences asterisk / struct node left, / left child asterisk / struct node right, / right child asterisk / tree node. This creates two new type keywords called tree node, a structure, and a pointer to treepter the structure. Then the routine talloc could become treepter talloc, void, return, treepter, malloc, size of, tree node. It must be emphasized that a typedef declaration does not create a new type in any sense. It merely adds a new name for some existing type. Nor are there any new semantics. Variables declared this way have exactly the same properties as variables whose declarations are spelled out explicitly. In effect, typedef is like hashtag define, except that since it is interpreted by the compiler, it can cope with textual substitutions that are beyond the capabilities of the preprocessor. For example, typedef int *pfi char asterisk creates the type pfi for pointer to function of two arguments, returning char asterisk int, which can be used in contexts like PFI strcmp nump in the sort program of Chapter 5. Besides purely aesthetic issues, there are two main reasons for using typedefs. The first is to parameterize a program against portability problems. If typedefs are used for data types that may be machine-dependent, only the typedefs need change when the program is moved. One common situation is to use typedef names for various integer quantities, then make an appropriate set of choices of short, int, and long for each host machine. Types like size_t and pretdef_t from the standard library are examples. The second purpose of typedefs is to provide better documentation for a program. A type called treepter may be easier to understand than one declared only as a pointer to a complicated structure. 6.8 Unions. A union is a variable that may hold, at different times, objects of different types and sizes, with the compiler keeping track of size and alignment requirements. Unions provide a way to manipulate different kinds of data in a single area of storage without embedding any machine-dependent information in the program. They are analogous to variant records in Pascal. As an example such as might be found in a compiler symbol table manager, suppose that a constant may be an int, a float, or a character pointer. The value of a particular constant must be stored in a variable of the proper type. Yet it is most convenient for table management if the value occupies the same amount of storage and is stored in the same place regardless of its type. This is the purpose of a union, a single variable that can legitimately hold any of one of several types. The syntax is based on structures. Union u_tag int ival, float val, char asterisk val. U. The variable u will be large enough to hold the largest of the three types. The specific size is implementation dependent. Any of these types may be assigned to u and then used in expressions, so long as the usage is consistent. The type retrieved must be the type most recently stored. It is the programmer's responsibility to keep track of which type is currently stored in a union. The results are implementation dependent if something is stored as one type and extracted as another. Syntactically, members of a union are accessed as union named member or union pointer dash member, just as for structures. If the variable u type is used to keep track of the current type stored in u, then one might see code such as if u type equals int printf %d \n u.ival. If u type equals float printf %f \n u.val. If u type equals string printf %s \n sval, else printf bad type %d and u type \n u type. Unions may occur within structures and arrays and vice versa. The notation for accessing a member of a union in a structure, or vice versa, is identical to that for nested structures. For example, in the structure array defined by struct char asterisk name int flags int u type union vint ival float val char asterisk sval u a simtab and swim, the member ival is referred to as simtab I do.ival and the first character of the string sval by either of asterisk simtab I do sval simtab I do sval 0. In effect, a union is a structure in which all members have offset 0 from the base. The structure is big enough to hold the widest member, and the alignment is appropriate for all of the types in the union. The same operations are permitted on unions as on structures: assignment to or copying as a unit, taking the address, and accessing a member. A union may only be initialized with a value of the type of its first member. Thus, union u described above can only be initialized with an integer value. The storage allocator in Chapter 8 shows how a union can be used to force a variable to be aligned on a particular kind of storage boundary. 6.9 Fields. When storage space is at a premium, it may be necessary to pack several objects into a single machine word. One common use is a set of single-bit flags in applications like compiler symbol tables. Externally imposed data formats, such as interfaces to hardware devices, also often require the ability to get at pieces of a word. Imagine a fragment of a compiler that manipulates a symbol table. Each identifier in a program has certain information associated with it. For example, whether or not it is a keyword, whether or not it is external and/or static, and so on. The most compact way to encode such information is a set of 1-bit flags in a single char or int. The usual way this is done is to define a set of masks corresponding to the relevant bit positions, as in hashtag define keyword 0, 1 hashtag define external 0, 2 hashtag define static 0, 4 or enum keyword equals 0, 1, external equals 0, 2, static equals 0, 4. The numbers must be powers of 2. Then accessing the bits becomes a matter of bit fiddling with the shifting, masking, and complementing operators that were described in Chapter 2. Certain idioms appear frequently. Flags equals external static turns on the external and static bits in while flags and equals external static turns them off, and if flags and external static equals 0 is true if both bits are off. Although these idioms are readily mastered, as an alternative, C offers the capability of defining and accessing fields within a word directly rather than by bitwise logical operators. A bit field, or field for short, is a set of adjacent bits within a single implementation-defined storage unit that we will call a word. For example, the symbol table hashtag defines above could be replaced by the definition of 3 fields, struct and signed int is underscore keyword 1, and signed int is underscore extern 1, and signed int is underscore static 1. Flags. This defines a variable table called flags that contains 3 1-bit fields. The number following the colon represents the field width in bits. The fields are declared and signed int to ensure that they are in signed quantities. Individual fields are referenced in the same way as other structure members. Flags is underscore keyword, flags is underscore extern, etc. Fields behave like small integers and may participate in arithmetic expressions, just like other integers. Thus, the previous examples may be written more naturally as flags is underscore extern equals flags is underscore static equals 1. To turn the bits on, flags is underscore extern equals flags is underscore static equals 0. To turn them off, and if flags is underscore extern equals 0 and flags is underscore static equals 0. To test them. Almost everything about fields is implementation dependent. Whether a field may overlap a word boundary is implementation defined. Fields need not be names. Unnamed fields, a colon and width only, are used for padding. The special width 0 may be used to force alignment at the next word boundary. Fields are assigned left to right on some machines and right to left on others. This means that although fields are useful for maintaining internally defined data structures, the question of which end comes first has to be carefully considered when picking apart externally defined data. Programs that depend on such things are not portable. Fields may be declared only as ints. For portability, specify signed or unsigned explicitly. They are not arrays and they do not have addresses, so the AND operator cannot be applied on them. Chapter 7. Input and Output. Input and output are not part of the C language itself, so we have not emphasized them in our presentation thus far. Nonetheless, programs interact with their environment in much more complicated ways than those we have shown before. In this chapter, we will describe the standard library, a set of functions that provide input and output, string handling, storage management, mathematical routines, and a variety of other services for C programs. We will concentrate on input and output. The ANSI standard defines these library functions precisely so that they can exist in compatible form on any system where C exists. Programs that confine their system interactions to facilities provided by the standard library can be moved from one system to another without change. The properties of library functions are specified in more than a dozen headers. We have already seen several of these, including styled H, stringed H, and typed H. We will not present the entire library here, since we are more interested in writing C programs that use it. The library is described in detail in Appendix B, 7.1 Standard Input and Output. As we said in Chapter 1, the library implements a simple model of text input and output. A text stream consists of a sequence of lines. Each line ends with a new line character. If the system doesn't operate that way, the library does whatever necessary to make it appear as if it does. For instance, the library might convert carriage return and line feed to new line on input and back again on output. The simplest input mechanism is to read one character at a time from the standard input, normally the keyboard, with getchar. In getchar, void returns the next input character each time it is called, or when it encounters and getchar EOF a file. The symbolic constant is defined and the value is typically -1. Bus tests EOF, a diode, H, should be written in terms of EOF so as to be independent of the specific value. In many environments, a file may be substituted for the keyboard by using the convention for input redirection. If a program prog uses getchar, then the command line prog in file causes prog to read characters from instead. The switching of the input is done in such an file a way that itself is oblivious to the change. In particular, the string is not prog in file, included in the command line arguments in argv. Input switching is also invisible if the input comes from another program via a pipe mechanism. On some systems, the command line other prog runs the two programs and pipes the standard output of into other prog the standard input for prog. The function int putchar, int, is used for output. Puts the character C on the which is by putchar, C, standard output, default the screen. Returns the character written, or is an error occurs. Again, putchar EOF output can usually be directed to a file with file name. If uses prog putchar, prog vout file will write the standard output to out file instead. If pipes are supported, prog another prog puts the standard output of into the standard input of prog another prog. Output produced by also finds its way to the standard output. Calls to and printf putchar printf may be interleaved. Output happens in the order in which the calls are made. Each source file that refers to an input-output library function must contain the line hashtag includes stio h before the first reference. When the name is bracketed by and a search is made for the header in a standard set of places, for example, on Unix systems, typically in the directory /usr/include. Many programs read only one input stream and write only one output stream. For such programs, input and output with getchar, putchar, and printf may be entirely adequate and is certainly enough to get started. This is particularly true if redirection is used to connect the output of one program to the input of the next. For example, consider the program lower, which converts its input to lowercase. Hashtag includes diode h, hashtag include type h main / lower, convert input to lowercase * and c. While c equals getchar equals EOF, putchar, tolower, c, return 0, the function tolower is defined in typed h. It converts an uppercase letter to lowercase and returns other characters untouched. As we mentioned earlier, functions like getchar and putchar in diode h and tolower in type h are often macros, thus avoiding the overhead of a function call per character. We will show how this is done in section 8.5. Regardless of how the typed h functions are implemented on a given machine, programs that use them are shielded from knowledge of the character set. Exercise 7-1. Write a program that converts uppercase to lower or lowercase to upper depending on the name it is invoked with, as found in argv 0. 7.2 Formatted output, printf. The output function printf translates internal values to characters. We have used printf informally in previous chapters. The description here covers most typical uses, but is not complete. For the full story, see Appendix B. Int printf, char * format, arg1, arg2. Printf converts, formats, and prints its arguments on the standard output under control of the format. It returns the number of characters printed. The format string contains two types of objects: ordinary characters, which are copied to the output stream, and conversion specifications, each of which causes conversion and printing of the next successive argument to printf. Each conversion specification begins with a % and ends with a conversion character. Between the % and the conversion character there may be, in order, a minus sign, which specifies left adjustment of the converted argument. A number that specifies the minimum field width. The converted argument will be printed in a field at least this wide. If necessary, it will be padded on the left or right, if left adjustment is called for, to make up the field width. A period, which separates the field width from the precision. A number, the precision, that specifies the maximum number of characters to be printed from a string, or the number of digits after the decimal point of a floating point value, or the minimum number of digits for an integer. An H if the integer is to be printed as a short, or L, letter L, if as a long. Conversion characters are shown in Table 7.1. If the character after the % is not a conversion specification, the behavior is undefined. Table 7.1 Basic printf conversions character. Argument type. Printed as d, int, decimal number o int, and signed octal number, without a leading 0, x, int, and signed hexadecimal number, without a leading 0x or 0x, using ABCDF or ABCDF for 10, 15, uint, and signed decimal number cint, single character s. Char asterisk, print characters from the string until a \0, or the number of characters given by the precision. F double, dash m dddd, where the number of Ds is given by the precision, default 6.
E.
Double, dash m dda plus / xx or dash m dddd plus / dash 20, where the number of Ds is given by the precision, default 6.
G.
Double, use %e or %e if the exponent is less than -4 or greater than or equal to the precision. Otherwise use %f. Trailing zeros and a trailing decimal point are not printed.
P.
Void asterisk, pointer, implementation-dependent representation. %no argument is converted. Print a %. A width or precision may be specified as asterisk, in which case the value is computed by converting the next argument, which must be an int. For example, to print at most max characters from a string s, printf, %*s, max s. Most of the format conversions have been illustrated in earlier chapters. One exception is the precision as it relates to strings. The following table shows the effect of a variety of specifications in printing hello, world, 12 characters. We have put colons around each field, so you can see it extent. %s, hello, world, %10s, hello, world, %.10s, hello, war, %-10s, hello, world, %.15s, hello, world, %-15s, hello, world, %15.10s, hello, war, %-15.10s, hello, war. A warning. Printf uses its first argument to decide how many arguments follow and what their type is. It will get confused and you will get wrong answers if there are not enough arguments of if they are the wrong type. You should also be aware of the difference between these two calls. Prints /* fails if s contains %/printf, %s, s, /safe * the function sprints does the same conversions as does, but stores the output in a printf string. In sprintf, char * string, char * format, arg1, arg2. Sprints formats the arguments in arg1, arg2, etc., according to format as before, but places the result in string instead of the standard output. String must be big enough to receive the result. Exercise 7-2. Write a program that will print arbitrary input in a sensible way. As a minimum, it should print non-graphic characters in octal or hexadecimal according to local custom and break long text lines. 7.3 Variable length argument lists. This section contains an implementation of a minimal version of printf to show how to write a function that processes a variable length argument list in a portable way. Since we are mainly interested in the argument processing, minprintf will process the format string and arguments, but will call the real printf to do the format conversions. The proper declaration for printf is int printf char *fmt, where the declaration means that the number and types of these arguments may vary. The declaration can only appear at the end of an argument list. Our minprintf is declared as void minprintf char *fmt, since we will not return the character count that printf does. The tricky bit is how minprintf walks along the argument list when the list doesn't even have a name. The standard header, starg h, contains a set of macro definitions that define how to step through an argument list. The implementation of this header will vary from machine to machine, but the interface it presents is uniform. The type va_list is used to declare a variable that will refer to each argument in turn. In minprintf, this variable is called ap. For argument pointer, the macro va_start initializes ap to point to the first unnamed argument. It must be called once before ap is used. There must be at least one named argument. The final named argument is used by va_start to get started. Each call of returns one argument and steps ap to the next, uses a type name va_arg to determine what type to return and how big a step to take. Finally, va_print does whatever cleanup is necessary. It must be called before the program returns. These properties form the basis of our simplified printf. Hashtag include starg h / minprintf, minimal printf with variable argument list */ void minprintf, char fmt, a va_list ap, / points to each unnamed arg and turn */ char *p, *val. Int ival, doubled val, va_start, ap, fmt, / make ap point to first unnamed arg * for p equals fmt, p if p equals %, a putchar *p, continue, switch *++p, a case d, ival equals va_arg, ap int. Printf, %d, ival, break, case f, dval equals va_arg, ap, double. Printf, %f, dval, break, case s, for sval equals va_arg, ap, char *, sval putchar, sval, break, default, putchar, *p, break. va_print, ap, / cleanup when done */ exercise 7-3. Revise to handle more of the other facilities of minprintf printf. 7.4 Formatted input, scanf. The function is the input analog of providing many of the same conversion scanf printf facilities in the opposite direction. In scanf, char * format, scanf reads characters from the standard input, interprets them according to the specification in format, and stores the results through the remaining arguments. The format argument is described below. The other arguments, each of which must be a pointer, indicate where the corresponding converted input should be stored. As with printf, this section is a summary of the most useful features, not an exhaustive list. Scanf stops when it exhausts its format string, or when some input fails to match the control specification. It returns as its value the number of successfully matched and assigned input items. This can be used to decide how many items were found. On the end of file, EOF is returned. Note that this is different from 0, which means that the next input character does not match the first specification in the format string. The next call to scanf resumes searching immediately after the last character already converted. There is also a function scanf that reads from a string instead of the standard input. In scanf, char * string, char * format, arg1, arg2, it scans the string according to the format in format and stores the resulting values through arg1, arg2, etc. These arguments must be pointers. The format string usually contains conversion specifications, which are used to control conversion of input. The format string may contain blanks or tabs, which are not ignored. Ordinary characters, not %, which are expected to match the next non-white space character of the input stream. Conversion specifications, consisting of the character %, an optional assignment suppression character *, an optional number specifying a maximum field width, an optional h. L or L indicating the width of the target, and a conversion character. A conversion specification directs the conversion of the next input field. Normally, the result is places in the variable pointed to by the corresponding argument. If assignment suppression is indicated by the * character, however, the input field is skipped. No assignment is made. An input field is defined as a string of non-white space characters. It extends either to the next white space character or until the field width is specified is exhausted. This implies that SCAMP will read across boundaries to find its input, since new lines are white space. White space characters are blank, tab, new line, carriage return, vertical tab, and form feed. The conversion character indicates the interpretation of the input field. The corresponding argument must be a pointer, as required by the call-by-value semantics of C. Conversion characters are shown in Table 7.2. Table 7.2. Basic SCAMP conversions character input data, argument type D decimal integer, int *I. Integer, int star. The integer may be an octal, leading 0, or hexadecimal, leading 0x or 0x. O octal integer, with or without leading 0, int *U and signed decimal integer, and signed int *x. Hexadecimal integer, with or without leading 0x or 0x, int *C. Characters, char star. The next input characters, default 1, are placed at the indicated spot. The normal skip over white space is suppressed. To read the next non-white space character, use %1ss. Character string, not quoted. Char *, pointing to an array of characters long enough for the string and a terminating \0 that will be added. E, F, G. Floating point number with optional sign, optional decimal point, and optional exponent. Float *% literal %. No assignment is made. The conversion characters D, I, O, U, and X may be preceded by H to indicate that a pointer to short rather than in appears in the argument list, or by L, letter L, to indicate that a pointer to long appears in the argument list. As a first example, the rudimentary calculator of Chapter 4 can be written with scanf to do the input conversion. Hashtag includes diode, hmain, / rudimentary calculator * double sum, v, sum equals 0, while scanf, %lf, and v equals 1 printf, \t%.2f \n sum plus equals v, return 0. Suppose we want to read input lines that contain dates of the form. December 25th, 1988. The SCAMP statement isn't day, year, char month name, 20, scanf, %d, %s, %d, and day, month name, and year. No and is used with month name, since an array name is a pointer. Literal characters can appear in the SCAMP format string. They must match the same characters in the input. So we could read dates of the form mm/dd/yy with the SCAMP statement, int day, month, year. Scanf, %d/%d/%d, and month, and day, and year. Scanf ignores blanks and tabs in its format string. Furthermore, it skips over white space, blanks, tabs, new lines, etc., as it looks for input values.
To read input whose format is not fixed, it is often best to read a line at a time.
To read input whose format is not fixed, it is often best to read a line at a time, then pick it apart with scanf. For example, suppose we want to read lines that might contain a date in either of the forms above. Then we could write, while getLine, line, size of line, 0 if scanf line, %d, %s, %d, and day, month name, and year, equals 3, printf, valid, %s \n line. / December 25th, 1988 form / elsif scanf line, %d/%d/%d, and month, and day, and year, equals 3 printf, valid, %s\n line, /mm/dd/yy form */else printf, invalid, %s\n line, / invalid form */ calls to scanf can be mixed with calls to other input functions. The next call to any input function will begin by reading the first character not read by scanf. A final warning: the arguments to and must be pointers. By far the most scamp common error is writing scanf, %d, n instead of scanf, %d, and n. This error is not generally detected at compile time. Exercise 7-4. Write a private version of analogous to from the previous scanf min printf section. Exercise 5-5. Rewrite the postfix calculator of Chapter 4 to use and/or to do scamp the input and number conversion. 7.5 File access. The examples so far have all read the standard input and written the standard output, which are automatically defined for a program by the local operating system. The next step is to write a program that accesses a file that is not already connected to the program. One program that illustrates the need for such operations is cat, which concatenates a set of named files into the standard output. Cat is used for printing files on the screen and as a general-purpose input collector for programs that do not have the capability of accessing files by name. For example, the command catx c prints the contents of the files and nothing else on the standard output x c. The question is how to arrange for the named files to be read, that is, how to connect the external names that a user thinks of to the statements that read the data. The rules are simple. Before it can be read or written, a file has to be opened by the library function fopen. Fopen takes an external name like xc or yc, does some housekeeping and negotiation with the operating system, details of which needn't concern us, and returns a pointer to be used in subsequent reads or writes of the file. This pointer, called the file pointer, points to a structure that contains information about the file, such as the location of a buffer, the current character position in the buffer, whether the file is being read or written, and whether errors or end of file have occurred. Users don't need to know the details because the definitions obtained from stio h include a structure declaration called file. The only declaration needed for a file pointer is exemplified by file *fp. File *fopen, char *name, char *mode. This says that fp is a pointer to a file and returns a pointer to a notice that fopen file is a type name, like not a structure tag. It is defined with a details of how file int typedef. Fopen can be implemented on the Unix system are given in section 8.5. The call to fopen in a program is fp equals fopen, name, mode. The first argument of fopen is a character string containing the name of the file. The second argument is the mode, also a character string, which indicates how one intends to use the file. Allowable modes include read, r, write, w, and append, a. Some systems distinguish between text and binary files. For the latter, a b must be appended to the mode string. If a file that does not exist is opened for writing or appending, it is created if possible. Opening an existing file for writing causes the old contents to be discarded, while opening for appending preserves them. Trying to read a file that does not exist is an error, and there may be other causes of error as well, like trying to read a file when you don't have permission. If there is any error, fopen will return null. The error can be identified more precisely. See the discussion of error handling functions at the end of section 1 in Appendix B. The next thing needed is a way to read or write the file once it is open. Gec returns the next character from a file. It needs the file pointer to tell it which file. In gec, file *fp returns the next character from the stream referred to by fp. It returns for end of file gec eof or error. Putc is an output function. In putc, int c, file *fp, putc writes the character c to the file fp and returns the character written, or eof if an error occurs. Like getchar and putchar, gec and putc may be macros instead of functions. When a C program is started, The operating system environment is responsible for opening 3 files and providing pointers for them. These files are the standard input, the standard output, and the standard error. The corresponding file pointers are called stin, stout, and stare, and are declared in stiout h. Normally stin is connected to the keyboard and stout and stare are connected to the screen, but stin and stout may be redirected to files or pipes as described in section 7.1. And can be defined in terms of and as follows: getchar putchar gek, pook, stin, stout. Hashtag define getchar, gek, stin. Hashtag define putchar, c, pook, c, stout. For formatted input or output of files, the functions and may be used. These scanf are identical to and except that the first argument is a file pointer that specifies scanf printf, the file to be read or written. The format string is the second argument. Int scanf, file *fp, char *format. Int prints, file *fp, char *format. With these preliminaries out of the way, we are now in a position to write the program cat to concatenate files. The design is one that has been found convenient for many programs. If there are command line arguments, they are interpreted as file names and processed in order. If there are no arguments, the standard input is processed. Hashtag includes stio, h/*cat, concatenate files, version 1*/main, int argc, char *argv, file *fp, void file copy, file file *. If argc equals 1, / no args, copy standard input / file copy, stin, stout, else while argc 0 if fp equals fopen plus argv, r equals null, a printf, cat, can open %s\n, *argv, return 1. Else file copy, fp, stout, close fp, return 0, / file copy, copy file ifp to file op * void file copy, file *ifp, file *op, rent c. Not while, c equals gek, ifp, equals zof, pook, c, op. The file pointers stin and stout are objects of type star. They are constants, however, file variables, so it is not possible to assign to them. The function int close file *fp is the inverse of fopen. It breaks the connection between the file pointer and the external name that was established by fopen, freeing the file pointer for another file. Since most operating systems have some limit on the number of files that a program may have open simultaneously, it's a good idea to free the file pointers when they are no longer needed, as we did in cat. There is also another reason for close on an output file. It flushes the buffer in which pook is collecting output. Close is called automatically for each open file when a program terminates normally. You can close stin and stout if they are not needed. They can also be reassigned by the library function freeopen. 7.6 Error handling, stare and exit. The treatment of errors in cat is not ideal. The trouble is that if one of the files can't be accessed for some reason, the diagnostic is printed at the end of the concatenated output. That might be acceptable if the output is going to a screen, but not if it's going into a file or into another program via a pipeline. To handle this situation better, a second output stream, called stare, is assigned to a program in the same way that and are. Output written on normally stin stout stare appears on the screen even if the standard output is redirected. Let us revise cat to write its error messages on the standard error. Hashtag includes stio, h, / cat, concatenate files, version 2 * main, int argc, char * argv, file *fp, void file copy, file file *, charprog equals argv0, / program name for errors */. If argc equals 1, / no args, copy standard input / file copy, stin, stout, else while, argc 0 if fp equals fopen plus argv, r equals null, a prints, stare, %s, can't open %s\n, prog, *argv. Exit 1. Else file copy, fp, stout, fclose fp. If forayer stout, print, stare, %s. Error writing stout \n, prog. Exit 2. Exit 0. The program signals errors in two ways. First, the diagnostic output produced by frint goes to stare, so it finds its way to the screen instead of disappearing down a pipeline or into an output file. We included the program name from argv0 in the message, so if this program is used with others, the source of an error is identified. Second, the program uses the standard library function exit, which terminates program execution when it is called. The argument of exit is available to whatever process called this one, so the success or failure of the program can be tested by another program that uses this one as a subprocess. Conventionally, a return value of 0 signals that all is well. Non-zero values usually signal abnormal situations. Exit calls close for each open output file to flush out any buffered output. Expr is equivalent to within has the advantage that it can be main, return exit expr. Exit called from other functions, and that calls to it can be found with a pattern searching program like those in Chapter 5. The function forayer returns non-zero if an error occurred on the stream fp int forayer, file *fp. Although output errors are rare, they do occur, for example, if a disk fills up, so a production program should check this as well. The function is analogous to it returns non-zero if end of file has fef, file *forayer, occurred on the specified file. Int fef, file *fp. We have generally not worried about exit status in our small illustrative programs, but any serious program should take care to return sensible, useful status values. 7.7 Line input and output. The standard library provides an input and output routine gets that is similar to the getLine function that we have used in earlier chapters. Char *gets, char *line, int maxLine, file *fp, reads the next input line, including the new line, from file into the character array gets fp at most characters will be read. The resulting line is terminated with line, maxLine, 1 \0. Normally returns on end of file or error it returns, returns the gets line, null. Get line length, which is a more useful value. 0 means end of file. For output, the function fputs writes a string, which need not contain a new line, to a file. Int fputs, char *line, file *fp, it returns EOF if an error occurs and non-negative otherwise. The library functions and are similar to and but operate on gets puts gets fputs, stin and confusingly, deletes the terminating and adds it. Stout. Gets \n, puts. To show that there is nothing special about functions like, and here they are, gets fputs, copied from the standard library on our system. / gets, get at most n chars from iop * char *gets, char *s, int n, file *iop, a register int c, register char cs, cs equals s, while n greater than 0 and c equals get iop, equals eof if cs ++ equals c, equals \n. Break, *cs equals \0, return, c equals eof and cs equals s. Null, s, a / fputs, put string s on file iop * int fputs, char *s, file *iop, and c. While c equals *s++, puk, c, iop, return for 8 iop, eof, 0. For no obvious reason, the standard specifies different return values for and forayer fputs. It is easy to implement R from getLine gets / getLine, read a line, return length * and getLine, char *line int max, if gets line max stin equals null, return 0, else. Return stolen line, exercise 7-6. Write a program to compare two files, printing the first line where they differ. Exercise 7-7. Modify the pattern finding program of Chapter 5 to take its input from a set of named files, or, if no files are named as arguments, from the standard input. Should the file name be printed when a matching line is found? Exercise 7-8. Write a program to print a set of files, starting each new one on a new page, with a title and a running page count for each file. 7.8. Miscellaneous functions. The standard library provides a wide variety of functions. This section is a brief synopsis of the most useful. More details and many other functions can be found in Appendix B. 7.8.1 String operations. We have already mentioned the string functions and found strlen, strcpy, strcat, strcmp. In the following, S and T are asterisk, S, and C and N are stringed H. Char ints. Strcat S, T, concatenate T to end of S stringcat, S, T, and concatenate N characters of T to end of S strcmp, S, T, return negative, 0, or positive for S less than T, st. S equals T same as but only in first N characters strncmp, S, T, N, strcmp strcpy, S, T, copy T to S strncpy, S, T, and copy at most N characters of T to S strlen's return length of S strchr, S, C. Return pointer to first C and S, or null if not present strchr, S, C. Return pointer to last C and S, or null if not present. 7.8.2 Character class testing and conversion. Several functions from type.h perform character tests and conversions. In the following, C is and that can be represented as an or the function returns int and signed char EOF.
Int.
Isalpha, C, non-zero if C is alphabetic, 0 if not isupper, C non-zero if C is uppercase, 0 if not ilower, C non-zero if C is lowercase, 0 if not isdigit, C non-zero if C is digit, 0 if not isalnum, C non-zero if isalpha, C, or 0 if not isdigit, C. Ispace, C, non-zero if C is blank, tab, new line, return, form feed. Vertical tab tuper, C. Return C converted to uppercase tallower, C. Return C converted to lowercase. 7.8.3 Unject. The standard library provides a rather restricted version of the function unject that we wrote in Chapter 4. It is called unject. Int unject, int C, file *fp, pushes the character C back onto file fp and returns either C or for an error. Only one EOF character of pushback is guaranteed per file. Unject may be used with any of the input functions like or scanf, gec, getchar. 7.8.4 Command execution. The function system, char *s, executes the command contained in the character string s, then resumes execution of the current program. The contents of s depend strongly on the local operating system. As a trivial example, on Unix systems, the statement system, date, causes the program date to be run. It prints the date and time of day on the standard output. System returns a system-dependent integer status from the command executed. In the Unix system, the status return is the value returned by exit. 7.8.5 Storage management. The functions and obtain blocks of memory dynamically. Malloc calloc. Void *malloc, size _tn, returns a pointer to n bytes of uninitialized storage, or if the request cannot be satisfied.
Null.
Void *calloc, size _tn, size _t-size, returns a pointer to enough free space for an array of n objects of the specified size, or if null the request cannot be satisfied. The storage is initialized to 0. The pointer returned by or has the proper alignment for the object in question, malloc calloc, but it must be cast into the appropriate type, as an int *ip. IP equals int *calloc n size of int. Free p frees the space pointed to by p, where p was originally obtained by a call to malloc or calloc. There are no restrictions on the order in which space is freed, but it is a ghastly error to free something not obtained by calling malloc or calloc. It is also an error to use something after it has been freed. A typical but incorrect piece of code is this loop that frees items from a list. For p equals head, p equals null, p equals p dash next, / wrong / free, p. The right way is to save whatever is needed before freeing. For p equals head, p equals null, p equals q, q equals p dash next free p. Section 8.7 shows the implementation of a storage allocator, like malloc, in which allocated blocks may be freed in any order. 7.8.6 Mathematical Functions. There are more than 20 mathematical functions declared in Math H. Here are some of the more frequently used. Each takes 1 or 2 arguments and returns a double-double. Sine of x, x in radian sine, x, cosine of x in radians cosine, x, addend 2, y, x, arctangent of y/x. In radians exp, x, exponential function x log, x, natural, base e, logarithm of x, x greater than 0, log 10, x, common, base 10, logarithm of x, x greater than 0, pow, x, y, xy sqrt, x, square root of x, x greater than 0, fabs x. Absolute value of x 7.8.7 random number generation. The function rand computes a sequence of pseudo-random integers in the range 0 to rand_max, which is defined in slib h. One way to produce random floating point numbers greater than or equal to 0 but less than 1 is hashtag defineFrand, double rand, / rand_max plus 1.0. If your library already provides a function for floating point random numbers, it is likely to have better statistical properties than this one. The function sets the seed for the portable implementation of srand and signed rand. Rand and srand suggested by the standard appears in section 2.7. Exercise 7-9. Functions like isupper can be implemented to save space or to save time. Explore both possibilities.